Okay, so first of all, we're going to review oscillations, and we're going to be able to add on to that. So, simple harmonic motion is periodic motion which can be described with a sine or cosine wave. For every one of these, there's going to be some restoring force that tries to bring it back to equilibrium. So it's Hookean, in other words. So this is that negative that we were talking about in Hooke's law, F equals negative kx. That negative we never really used for any calculations, but now we're going to talk about why that is important. Well, it's because it's bringing it back. It's trying to bring it back to equilibrium point. So for everything in a simple harmonic oscillator, if you displace it from equilibrium, it's going to be trying to come back to equilibrium, and it'll maintain that sinusoidal relationship. So let's review first some of the ones we've already found. So for instance, let's say the Earth going around the sun. We know the net force is going to be caused by gravity. In this case, the reason I'm putting G prime here is because it's not 10, it's just some other local gravitational field. And of course, the net force for circular motion is mv squared over r. And I can solve this for v squared, which would be equal to r g prime. And of course, the speed is given by a kinematic relationship of distance divided by time, so 2 pi r divided by t, and square that. And then I can solve this, rearrange and solve it for t squared, and I get t squared equals 4 pi squared r over g prime. That is the relationship for planets going around stars. And I hope that makes sense. The further out that it is, the bigger the r is, then the more time it takes to go around. And the smaller the local gravitational field strength, so the less strong the gravity field is, then the more time it takes as well, because of the inverse relationship. We also have a couple other relationships. For a simple pendulum over here on the left, we found t squared is equal to 4 pi squared L over G. And for a spring, we found it was t squared equals 4 pi squared M over K. I hope both of those make sense too. The longer the simple pendulum is, the more time, and so the stronger the gravitational field constant, the less time. And then for a spring, the bigger the inertia, the more massive it is, the lazier it is, the more time. And the bigger the spring constant, the stiffer the spring is, the less time. Well, I want to derive these, okay? So we should be able to derive these as well. If we're looking at this pendulum as it swings through an arc length of x with an angle theta. And of course, we know for circular motion that the arc length, in this case x, would be given by r theta, where r is the length of the pendulum, so L theta. And we also know that there's a component of the gravity that's trying to bring it back to equilibrium down here at the bottom, and that's mg sine of theta. I'm going to put a negative on there because it's trying to bring it back toward that point. We want to know if this is a Hookean relationship, like the F equals negative kx. Well, that would be true. This F equals negative mg sine of theta, this would be Hookean as long as theta is proportional to sine over theta, which is only true for very tiny angles. So sine of theta, again in radians, is pretty close to theta for small angles. So we're starting off with F equals negative mg sine of theta, and let's assume this is small angles, so therefore it's approximately negative mg theta. Again, we're dealing with radians here. We know that theta is the arc length divided by r, which is L in this case. So we have negative mg over L times x. Now think about what F is. F equals ma. Now let's divide both sides by the mass, and I get negative g over L times x. Now, we're going to do a little bit of calculus here. Acceleration is really the second derivative with respect to time of the position. It's kind of a brain teaser you need to think about really hard for people who are in calculus. You need to think of some function that when you take the derivative of it twice, gives you that same function except there's a negative. Think of some function, you take the derivative not once, but twice, and you get the same function again except it's negative. Well, there's only two functions like that we know of in calculus, and those are sine and cosine. So let's set x equal to some generic cosine function. I'm going to say a is the amplitude. Again, I'm just making up a generic cosine function. I could have chose sine, But let's say this cosine curve has some amplitude A, and it has some angular speed, omega times t. In other words, this omega is going to be how long it takes for it to go through one period of motion, so 2 pi radians in a period of big T, okay? This phi over here, this is called the phase constant. It's how much out of phase. In other words, it doesn't have to be starting with this motion of sinusoidal. It doesn't have to be starting at 0 radians. It could be starting at pi over 3 radians or pi over 6 radians or some, whatever, negative pi over 6 radians. It doesn't have to be at 0. So I'm just making a generic cosine function. Okay, so what would the velocity be? Well, velocity would be the slope of this, or in calculus terms, the derivative of this as a function of time. And again, omega is it's sometimes called the angular speed of this, and it goes through 2 pi radians in a time period of capital T. That's the period. So the time rate of change of this, the velocity, would be equal to, well, the derivative of this function with respect to time. Well, that would be negative sine omega t plus v. And then, of course, I have to take the derivative of omega t, which is omega. So I end up getting negative a omega sine of the quantity omega t plus v. Let's find the acceleration, which is the derivative with respect to time of the velocity, or the second derivative of the position vector. Well, if I take the derivative of this function with respect to time, the derivative of sine is cosine. And the derivative of omega t is just omega. So I end up getting negative a omega squared times cosine of the quantity omega t plus v. All right, so now I know what my x and my a is, because I'm going to plug that in this equation. So here's my x, here's my a, some generic cosine function. Let's plug that in. So this is my acceleration that I found through calculus. This is just my generic function. Look at these two sides. There's a lot in common that we can cancel. For instance, the amplitude doesn't even matter. I can cancel that out. I can cancel out the negative. And I can cancel out the cosine of omega t plus v. And so I end up getting omega squared is equal to g over L. Again, remember omega squared, omega is kind of like the angular speed of this. It tells you, how quickly it goes through one period of motion, 2 pi radians. So omega is really 2 pi over the period t. So let's plug that in and square it, and we get t squared, when we solve this, t squared is equal to 4 pi squared L over g. Oh my gosh, that's the equation we already knew. Let's look at a Hookean spring. Let's do the exact same thing. So looking at this, F equals negative kx. So F again is equal to ma. And so I can solve this for the acceleration, which is the second derivative of x with respect to time. And I get the following. Again, notice the second derivative of x with respect to time gives me some negative x. Again, the only thing that qualifies would be a cosine or a sine function. Let's say a equals our generic cosine function. And that means we can solve for velocity. We get this sine function, and then solve for the acceleration, and we get this cosine function again. Let's plug that into this equation. We now know what acceleration is. We now know what x is. Let's plug that in. And this is what I end up getting. Notice the negative a, which is the amplitude again, cancels out. The cosine of omega t plus v cancels out, and I'm left with omega squared equals k over m. Remember, omega is the angular speed of this. It tells you how quickly it goes through 2 pi radians. So 2 pi divided by the period is what omega is. So now I can go ahead and solve this for t squared, and I get t squared is equal to 4 pi squared m over k. Oh my gosh, that's something we knew already. All right. Okay, so there are two that we've never seen before. And these have to do with kind of this unit looking at rotational inertia and torque. One's is called a physical pendulum. It's called a physical pendulum because not all the mass is concentrated in a bob at the bottom here. It's throughout the entire thing. So let's say a baseball bat. Could be a meter stick. Could be a pencil. Could be a pendulum on a grandfather clock because the mass isn't concentrated at the very bottom. Another one's called a torsion pendulum, and what that is this thin wire here, and we twist this bottom part here a little bit and let it go, and it kind of goes back and forth. For the physical pendulum, there's going to be a torque on this, and the torque is equal to negative mg, that's the force, times the distance away from the pivot point, in this case h, times the sine of the angle. Remember that torque is also equal to I alpha. For a torsion pendulum, the torque will be equal to negative k, some constant, times how far we displace it, theta. And again, remember that torque is also equal to I alpha. I want to show you a video of a torsion pendulum so you can kind of see what it looks like. You might have seen these on a clock before. And they just kind of go back and forth like this. That's a torsion pendulum. All right, so let's start with the physical pendulum. So we're starting off with this relationship here. Again, the torque would be from this force of weight, and this displaced from the pivot point way up here that we're holding it. That's pinned, so it can't move. And then this angle in between the two, so sine of theta. Let's assume that the angle is kind of small, so therefore sine of theta is equal to theta. So that means the torque is equal to mgh theta. Well, this is Hookean because it's directly proportional to the displacement, in this case theta. Torque is also equal to I alpha. So now solving this for alpha, I get alpha is equal to negative mgh over I times theta. Alpha is really the second derivative of theta with respect to time. Okay, well, what function where I take the second derivative gives me negative of the function? Well, that would be cosine or sine. So let's say theta t is equal to a times a generic cosine function. And again, the first derivative, which is the angular velocity, is equal to negative a omega sine omega t plus phi. And the second derivative, which is the acceleration, would be negative a omega squared cosine omega t plus phi. Plug in my acceleration, plug in my displacement, and I get the following. And notice a lot of this cancels. I'll get omega squared equals mgh over I. Plug in that omega is really the angular speed of this, which goes through 2 pi radians in a time period of 1 period. Solve this for t squared, and I get t squared is equal to 4 pi squared I over mgh. So see if this makes sense. As the rotational inertia gets bigger, so it's lazier, the time gets bigger. That makes sense. And as the torque, because that's basically a torque there, as the torque gets bigger, that means it has more ability to cause angular acceleration, then the time would get smaller because it's going through there faster. So yeah, that makes sense. All right, one more. Let's look at the torsion pendulum. So again, in this case, the torque is equal to negative some constant, which is related to the stiffness of the wire, times the angle through which it's displaced. In this case, some theta max, let's say. Don't forget, we also know that torque is equal to I alpha. So solving this for alpha, we get alpha is equal to negative k over I times theta. Well, remember alpha is really the second derivative with respect to time of theta. And so the only functions that work this way are cosine and sine. So let's use our generic cosine function. Take the derivative of it, find the velocity. Take the derivative again and find the acceleration. Plug in for the acceleration and plug in for the displacement. I get the following. I can cancel quite a bit. I get omega squared is equal to k over I. Again, omega is the angular velocity of this, if you will. It tells you how quickly it goes through 2 pi radians in this sinusoidal relationship. So that's going to be 2 pi over the period squared equals k over I. Solve this for t squared, and I get t squared equals 4 pi squared I over k. Again, the bigger the rotational inertia, the laziness of this, the more time it is. And the bigger the stiffness constant is, that would be the faster it goes back and forth, so that's less time.